Welcome back. So we are continuing with the heterocyclic compounds. We finished pyridine, now we'll start with pyrroles, okay? So pyridine, what we saw is that the Huckel's rule, 4n plus 2 rule is already followed. And then there is nitrogen with extra lone pair of electron. And that nitrogen is sp2 hybridized. And the p orbital containing the lone pair is orthogonal to the pi bonds. Therefore, it does not take part in resonance. But when you see 5-membered ring, okay, something like, we'll take example of pyrrole. So pyrrole is 5-membered ring, 1, 2, 3, 4, 5. And then there is nitrogen. Now, very important part is, this nitrogen is sp3 hybridized. So this lone pair is not like perpendicular to this pi bond. This pi bond is here. This pi bond, you understand, this p orbital is perpendicular to this paper, standing up like that and going below the paper. So all these are on the plane of paper. Now this one is not that this is like that, sleeping on the paper. No. If it was that case, then it cannot overlap with this. But this one is not exactly parallel to this also, but little this side it is little bit angular, but still it overlaps quite well with this p orbital, this p orbital, this p orbital, this p orbital. So appreciate this p orbital is something like this, and other two are other four are standing exactly parallel to each other. So they overlap, and now when it overlaps, what happens? Now the ring will have 6 pi electrons. 1, 2, 3, 4, 5, 6. So now it follows all the rules of aromaticity. What are the rules? It is cyclic, right? It is planar. Nothing is up and down. It's all in one plane. It's conjugated. All the p orbitals. Conjugation means all the neighboring atoms should have p orbital. Okay, so this is p orbital, this is p orbital, this is p orbital, this is p orbital. And all of them share the electron density. So it's conjugated, and most important, it is following Huckel's rule. It is having 4n plus 2 electrons. It is having 6 electrons. 1, 2, 3, 4, 5, 6. So 4n plus 2 electrons. So it is aromatic. Okay. So they are quite. So if it is aromatic, you know, benzene undergoes electrophilic substitution. Pyridine does not undergo, but this one undergoes electrophilic substitution. Unlike pyridine. Pyridine, what we saw, pyridine does not undergo electrophilic substitution. Why? What we said is, because pyridine has nitrogen, so quite electronegative. So we said it pulls away the electron cloud, and therefore quite a reduction in electron density from the ring, and therefore it is not able to give. Then you can ask the question, this also nitrogen is there, then why it is able to give? Important part is here, the nitrogen has little bit of minus I effect, but most importantly it is showing plus R effect. It is pumping electron. Any day plus R effect will be much stronger than minus I effect, right? There the nitrogen was not able to pump its own electron. Here the nitrogen able to pump electron. Not only that, it is 5-membered ring, so ring size is reduced. So it is able to drastically, so the ring electron density is drastically increased. So it is able to easily undergo electrophilic substitution reaction. So when you think about electrophilic, you should think about E plus is coming. Think about E plus is coming, and then this electron will go and attack, right? And then hydrogen will be replaced with this E. Now question is, at which position it happens? So first you should know the numbering. So the nitrogen gets first numbering, Pyrrole gets second, then third, fourth and fifth, right? So if you see the mechanism, imagine if electrophile is there. What you will feel is, if electrophile is there, what you will feel is, this lone pair will first come here, so you get a bond here, and this will move and you will attack the E plus. Okay? But that does not happen. What happens is, it comes here, you get a negative charge here, and then this comes here and you get a negative charge here. So you can also think if E plus is there, E plus can attack here, right? So these two I am drawing separately. Now, if we are given a choice, if you think from chemistry point of view, where electrophilic substitution should be easy, at this position or this position. So understand, how fast the reaction is undergoing is ruled by the kinetics. That means how stable is the intermediate. If the intermediate is stable, then activation energy is low, reaction is fast. Now you see here, if attack is here, the negative charge is not getting stabilization, but when attack is on here, you are getting negative charge stabilization. Lone pair is coming here, then coming here, here, here. So the electron cloud is moving throughout and gives stabilization, right? And therefore electrophilic attack happens either at position 2 or position 5. Okay, so first it comes here and you get negative charge here, and then negative charge moves in, you get a negative charge here, and then you can finish the ring. Okay, and then it comes back here, this comes here, you get a negative charge here, and then it moves here, comes here negative charge, then it comes back, and you get here, you get pyrrole back. Okay, so all this you practice. It's a very simple thing. So what I am trying to say is, remember this always, attack will not happen on, see, after all these two positions are identical, so attack will happen either here or here. Attack will not happen at here, and it is very confusing. Generally people end up thinking attack will happen here. Okay, it's a very favorite question in all the competitive examinations, right? Now let us see. Now this benzene ring, this pyrrole ring, it is highly activated. No, just now I talked that electrophilic substitution happens at position 2 and 5. But you do see, example, you are doing bromination at 0 degrees Celsius. That means, 0 degrees Celsius, quite low temperature. You are not pushing the reaction. Still at 0 degrees Celsius also, it is bromination is happening at 4 position hydrogen going. So it's quite a reactive species. So one thing is, if it is aromatic, it should be more stable. Okay, that means it should be less reactive. So we know little bit it's less it is less aromatic. It's not very aromatic, because but still it is aromatic. If it's quite aromatic, I will say, because if it was, especially if it stops undergoing electrophilic substitution reaction, it starts undergoing addition reaction. That means this double bond is lost and you are getting attack. Then you say that aromaticity is very, very low. But still it is undergoing electrophilic substitution reaction. Therefore, it is still very aromatic. But if I compare something like pyridine, I can say it is less reactive, less aromatic, because it is more reactive than pyridine, right? And we'll see more examples. You'll get the idea. And apart from that, what it says is we have to be very careful about what kind of electrophilic substitution reaction we do. We cannot do electrophilic substitution reaction where strong acid is needed. So in which reaction strong acid is needed? Electrophilic substitution, nitration. So in nitration what we do? We use HNO3 and H2SO4, right? So that we get NO2 plus. Now these both are very strong acid. In presence of strong acid undergoes polymerization. This undergoes polymerization, and therefore you cannot carry out reactions where electrophilic substitution reaction where strong acid is used. So polymerization reaction, it is showing the mechanism. First attack is happening at position number 5 or 2, whatever you call it, 1, 2, you can say 2 only, and then this lone pair comes and attacks here, it comes back here, things like that, it keeps moving. Okay, I have talked quite a lot about it. Once again I will show you. See, attack will not happen at position 3 because kinetically unfavored. Here it is kinetically favored. This comes here, this comes here, this comes here. So at position number 2 or 5, whatever you call it, so your attack happens at position number 2. Is it very clear? Right. Okay, now this is very important reaction. This is Wills-Meyer-Heck formylation reaction. Okay, so whenever named reaction is there, generally mechanism is also needed. So for this reaction also mechanism is needed. Remember this in chemistry. In chemistry, the chemists always love this named reactions, because named reactions never change. Everything else in chemistry keeps changing because it's still developing. But when a reaction gets a name, that means it is very, very well established reaction, it hardly fails. If I see a paper, this reaction they have done, if I carry out, I straight away start from the beginning, 50% chance it won't happen. But if I do some textbook named reaction, I'm almost 100% sure that this reaction will work, okay? So this is Wills-Meyer-Heck formylation reaction. So from the name you can understand it is formylation. Formyl is CHO. So addition of CHO group. And again, if it is pyrrole, attack will happen at position number 2, okay? So here what you do is you take DMF. Now DMF is very important. Many times I have told before, again I'll tell you. DMF is a very, very important solvent. Its boiling point is around 150 degrees Celsius, okay? One of the best solvents to carry out SN2 reactions. Not one of the best, the best solvent to carry out SN2 reaction, okay? Because it is non-aprotic but polar solvent, is highly polar solvent, and it is aprotic. It's not like methanol which can give a proton, right? So DMF, you should know the full form, so that remember that N dimethyl. So on N, 2 methyl groups are there. N dimethyl formamide. So you are having CHO. CHO is there and NME2 is there. So what is the functional group? Anybody? So this functional group is amide. So this was amine which has reacted with acid or acid derivative, and what you get is amide, okay? So DMF is nothing but an amide. It is N dimethyl formamide. So when you have pyrrole and you react with DMF in presence of POCl3 and sodium bicarbonate, what you are getting is at position 2 you are getting CHO, okay? So this is called as Wills-Meyer-Heck formylation reaction. Okay, this is a very favorite question GATE. I have seen many times this question they ask, okay? So this mechanism. Now interesting part is when they ask mechanism, they cannot ask you a whole mechanism because it is objective question. So they'll ask you some intermediate. What is the most important intermediate? So if you think that I will remember only intermediate and go, that's not possible because hundreds of reactions will be there. So once you know the reaction, you can draw the intermediate first, right? It says you can also take derivative of DMF and you can get similar product. So instead of DMF and then dimethyl formamide, you can put R here, okay? So instead of H, R is there, and then you carry out same reaction, you are able to put R, C double bond O at this position, okay? This is also modification of Wills-Meyer-Heck formylation reaction. So mechanism. So mechanism, first POCl3 reacts with DMF, okay? So DMF is not only solvent, is also a reactant here, remember that, okay? So first is DMF reacts with POCl3. So it's very simple, nitrogen lone pair comes in, this one attacks phosphorus, it is goes up, comes down, and Cl minus is lost. And then this Cl minus attacks and this leaves, and this is the most important intermediate. So they ask you what is the reactive species which react with pyrrole in Wills-Meyer-Heck formylation reaction. So you have to remember this intermediate, this Cl is there, it's a imine, C double bond N, okay, amine but double bond, so it is imine. So this is the most important intermediate which they ask in competitive examinations, okay? Now pyrrole is there, of course. So pyrrole goes and attacks, attack at position number 2, attack happens, and this goes up and this comes down, Cl minus is lost, and you are having this and you get this. And then this one mechanism, generally they don't show. If you want you can show also. Hydrolysis and all is taken for granted that you know the mechanism. So once you do hydrolysis of this imine, you get ketone back, okay? So remember, imine, whenever imine is there, very unstable. Imines are very unstable. Imine means amine with double bond. So imines, when you do hydrolysis with acid H3O+, you get back your ketonic group. So this is the mechanism important, okay? Now there is another reaction, Manic reaction, which we have done previously. So Manic reaction also what we use is formaldehyde. You have to remember this, okay? Manic reaction you have to use formaldehyde, and you use secondary or primary amine. You cannot use tertiary amine. We have done this. So here what happens? Water is lost. So how water is lost is H from this one, H from this one, and O from this one. H2O is lost, okay? So this CH2 goes in between. So this is there, CH2 goes in between, that hydrogen is gone, this hydrogen and this hydrogen also gone, and NME2 is joined, okay? So this Manic reaction we have done the mechanism previously. we don't need. Okay, then we'll see the similar analogues. So oxygen and sulfur analogues. So 6-member ring we have done heterocyclic. First one we did is pyridine, and 5-member ring first one we did is pyrrole, or rather pyrrole. And now when you have oxygen, it is called as furan, and we have sulfur, it is called as thiophene. So now you see this reaction. So when you are having oxygen, this is furan, you react with acetic anhydride. So this is electrophilic substitution reaction. Which reaction? Anybody? This reaction is Friedel-Crafts acylation reaction. AC2O means acetic anhydride. I hope everybody knows the formula. Okay. So acetic anhydride, I will write the formula for you. CH3 C double bond O. This is aceta part. Then O. If I put OH, it becomes acetic acid. But acetic anhydride means 2 acetic acid has come and water is lost. So another this one comes C double bond O CH3. Is it very clear? Now what happens? This will go, this will come here, this will come here, and this will attack at position number 2, and this one leaves, and ZnCl2 is a Lewis acid which catalyzes Friedel-Crafts acylation reaction. So you're getting this. So you see, important thing is at oxygen, when it is furan, reaction is happening only at 0 degrees Celsius. But when you are having sulfur, this is thiophene. This is very important. Okay, another very important heterocyclic compound. Thiophene, this reaction occurs at 100 degrees Celsius. Same mechanism. This will go here, this will go here, this will go and attack the this part. Okay, this part, this will come up, this will go down. Let me write the mechanism for you. This comes here, this comes here, this will go attack here, then this comes up, this goes down, and this one leaves. Okay, so when you do with sulfur, it is happening at 100 degrees Celsius. That means this thiophene is much lesser reactive than furan, and therefore actually thiophene is more aromatic than furan because it is more stable, it is less reactive. Now tell me the reason why is this less reactive than this? Because sulfur is not able to pump electron as good as oxygen is able to pump. Then you ask why? Because sulfur, if you see the atomic number, it is 16. So it is 286. So the lone pair of electron is in the 3p orbital, whereas carbon has pi electrons in 2p orbital. Now 2p and 3p orbital cannot overlap very well. 2p and 2p will overlap very well because energy is same, but 2p and 3p will not overlap very well, and therefore it is not able to donate electrons very effectively. And so the ring density, the electron density in the ring is not as high as this. Is it very clear? And therefore this reactivity is lesser. And now if I tell you between this and pyrrole and pyrrole, if I give you, tell me which will be more reactive, furan or pyrrole. One thing is very clear, this will be much lesser reactive than this also, because nitrogen also has lone pair of electron in 2p orbital. This also has lone pair of electron in 2p orbital. So think and tell me which will be more reactive, pyrrole or furan. Okay, we'll see the answer in the next page. Okay. Okay, so this one is more reactive. Now if you carried out that acetylation reaction which you saw, it might have happened at all the 4 positions for pyrrole, because you understand this, compared to oxygen and nitrogen, nitrogen is much lesser electronegative than oxygen. Okay, so what happens? Nitrogen electron, this lobe containing lone pair is much bigger, and oxygen's lone pair, the lobe containing lone pair is very small. So this is not able to give electron as effectively as this is giving. Is it very clear? So this one gives more effectively, and therefore and therefore the ring density on this is much more increased than this one. So if you see the reactivity, you will say that pyrrole is more reactive than furan than thiophene. If you just go by reactive, sometime back I said if it is less reactive, that means it is more aromatic, more stable. So you'll say that this is most aromatic than this one, than this one. But it's not just reactivity, we have to look at more important thing. Does it undergo addition reaction or electrophilic substitution reaction? Important thing is neither this nor this will ever undergo addition reaction, because they both are highly aromatic. This is least aromatic. Okay, this is very important, very important. It can undergo addition reactions. We'll do about it just now. So I said attack happens in position 2 or 5. You see this special one reaction I have said. If position 2 is already occupied, then if you do another electrophilic substitution reaction, this is nitration, then what happens? It will happen at position number 5, but it will not happen at position 3 and 4. It happens at 2. If 2 is occupied, then it comes and happens at 5. Okay. Now, if you see this reaction, okay. So in Pyrroles also we saw that when you do bromination, you get bromination at 4 position. Here also get. But when you do bromination methanol, in Pyrrole also we did bromination methanol, ethanol we did. Here when you are doing in methanol, you are getting addition product. See, the double bond is lost, the aromaticity is lost. You know, the bonds are lost. You are adding 2 groups. It's not that you have replaced hydrogen with OMe. Hydrogen is still there and you have added OMe. Hydrogen is still there and you have added OMe. So it is undergoing addition reaction, because remember this again, furan is least aromatic among all the heterocyclic compounds. Okay. So when you do bromination, this is the mechanism. First it will go and attack. This you come here, you get bromination, then methanol comes and attacks here, you get a positive charge here, and then this comes here and it forms acetal. Okay, the oxygen positive charge, and then this methanol comes in here, attacks here, and you get here. Right? So now this is the ultimate line which comes in. This is the favorite question of all competitive examination. Order of aromaticity is benzene is most, then comes pyridine, then comes thiophene. Remember, thiophene was least reactive, okay, because 3p 2p are not able to overlap, but they are following all the rules of aromaticity and very stable. It never undergoes addition reaction, it always undergoes electrophilic substitution reaction. And then comes pyrrole, and then comes furan. Furan is least because it undergoes addition reaction. Okay, see you, bye.